fiber, silicon wafers, semiconductors. These need to be American-made materials, and it just turns out the best place to make them is like above America, not in America. What we're doing with Outpost is building autonomous space factories. We're building a returnable platform that can go into space and come back to Earth with incredibly high precision and shipping container size payloads. The best way to do that is to have a very low ballistic coefficient reentry. We'll be subsonic around 90,000 feet. That's our first stage of our system, is a deployable heat shield. By 65,000 feet, we open our paraglider. It's a single surface ripstop nylon fabric. The paraglider has like a 10-to-1 glide ratio. A parafoil is like 3-to-1. So with a robot flying it, you can control it. And this is like advice to anybody who's starting a space company. There's a very good chance NASA already thought of your idea probably 30 years ago. So figure out who it is at NASA that did the research, wrote the paper, and go befriend them. And that's what we did here.
Thank you so much for joining us. I'm very excited for this conversation. We get to talk about not one, but two space companies.
That's right.
Would you mind telling us what's the current one you're building and how you got there?
Sure. Thanks for having me. So right now I'm building Outpost, and what we're doing with Outpost is building autonomous space factories. And the idea there is we're building like a returnable platform that can go into space and come back to Earth with incredibly high precision and very large payload capacity. So think like shipping container size payloads.
Damn. Yeah, that's so I know of a couple of return vehicles, of course. There are some things like we now know it is possible to launch a rocket for it to come back to Earth and land and survive. Like historically, the only thing that did that, I guess, was like the space shuttle. Is that the like earliest return thing, I guess? I don't know, they're like repeated return vehicle.
Right. So I guess you had like space shuttle, obviously capsules.
Sure.
We've had space capsules. It's funny that like this is the First Principles podcast, because a lot of the idea for Outpost was going back to first principles. If you were to make a returnable vehicle today, and your focus was high payload capacity and incredibly high precision on return, like landing pad precision, how would you do that? And from a like blank slate, we built up this idea, so it looks very different. It's not a capsule. It's not a space plane.
Yeah. We'll get into the depths of like exactly what it is and exactly why you chose the requirements you did and all that sort of stuff. I think that your origin story is particularly interesting though, because this is not your first rodeo. You've built things for space and you've built things in space before. So would you mind telling us about your first company and what that story was there?
Yeah, this is at least my second rodeo.
At least.
So the company that I think I'm most well known for, and the last one I built, was called Made in Space. We started that in 2010 and really kind of created the space manufacturing vertical. At the time, it was science fiction. There was like some pretty nice NASA papers from the like 70s about space manufacturing, but nobody had done it. And 2010 was like MakerBot had just come out. I think the patent for FDM 3D printing just expired, and MakerBot created this balsa wood 3D printer. And we had this idea of, well, what if you put one of those on the space station? And we had an astronaut friend who had been on the space station a few times and said, you know, we fix everything up there with duct tape, and a balsa wood 3D printer would be better than what's already up there. So we went to NASA, kind of convinced them that we should put a 3D printer on the space station. And I think by the time we had the first printer up, most of the world was just learning what 3D printers were. So they were like, how are you already on the space station with one of these? And so that was manufactured the first parts ever built off Earth. Did some
pausing there, that's unbelievable. Like, what a cool thing to say. Like, well, what was the first part?
Oh my God.
The first ever thing manufactured off Earth.
We're beyond the 10-year mark of this, and I kept that one quiet for a while because we got our hands slapped with what the first part was, and NASA actually, like, they kind of hid the story. And
really?
So that was a big deal for us. Like, what is the first thing humanity manufactures off planet Earth? Seemed like a important thing to figure out. And I will start with, like, this first mission was a partnership with NASA. So we, and this is like advice to anybody who's starting a space company. There's a very good chance NASA already thought of your idea probably 30 years ago. So figure out who it is at NASA that did the research, wrote the paper, and go befriend them. And that's what we did here There was a researcher at NASA Marshall who had the idea for putting 3D printers on the space station. So it ended up being a partnership, and we built and flew that that printer. Made in Space built it. NASA Marshall helped facilitate getting it on the space station, and so together we worked on what would that first print be. And it was pretty important. Thought like what all the different meaningful aspects about that, and what we landed on was we would have the printer print a part of itself. And this is like an homage to the self-replicating machine, or Freeman Dyson's Astro Chicken, if anybody knows that one. But it was basic. It was a pretty easy print. It was a plate that would cover a part of the printer, so it was easy. It wouldn't fail. An easy print. You could get a lot of information from this print when you get it back on Earth, like measure parts of it and things. And what we did was we put the Made in Space logo on it and the NASA worm logo. So we just thought we should put our logos on this. We got through the entire approval process. We flew the printer. All that stuff happened, and it came time for that first print. We printed it, and Butch Wilmore, the astronaut running the printer, did what he had to do. He holds up the print to the camera. That's how we would inspect it before anything else. And he holds up the print, and we're in our mission control watching it. And then NASA cuts the feed, and the phone rings, and it's NASA, and they're pretty upset, and they're like, who gave you approval to do this print? And we're like, what are you talking about? Like, we did this with NASA. And it turns out that at the time, this may have changed, but at the time, the NASA worm logo could only be used if the administrator of NASA gave approval for it to be used.
Wow.
So
was this meaning in favor of the meatball, or just like you can't use NASA's logo at all?
I think the meatball maybe was okay, but the worm had some sort of like,
wow,
you couldn't use it unless the administrator said you could. So the feed got cut. The NASA kind of like image repository from ISS of the day, like literally those image files were missing.
Oh
and then the story never got told. And one reporter, still to this day, like one reporter was somehow captured the feed image and wrote a story, and that image is on the internet. So it's part of why I share it, because like there's always been a news article about it, and you can find that image in one place. But then what happened was we still needed a good story to tell, and somewhere like maybe a couple weeks after we started printing, we're in our mission control, and we overhear Butch mention that he had lost a socket wrench on the space station. And at the time, I remember being like, how the heck does an astronaut lose something like that on the space station? But if you go look at photos of like the ISS, it's not that like clean walled, 2001 Space Odyssey. It's like, it's a very messy place, and things go missing. And I later found out like there's literally a musical keyboard missing on the space station. Like,
really,
they've just misplaced a musical keyboard. So stuff gets lost. So we heard that, and we called NASA that day and said, listen, we heard Butch has lost this socket wrench. What if we design one that could be 3D printed? Is there any way we could get that uplinked to the printer and print it? And they said, sure, why not? So we, in a matter of like a day, one of our engineers designed an actual like ratcheting wrench with a little leaf spring inside, all 3D printed in one part. Took it through tons of iterations, as you can imagine, with a 3D printer. Then we overnighted it to NASA, who for the first time held like a tool in their hand that they were deciding if they could qualify it for the ISS, but it wasn't the actual thing. It was like, right, we would send the digital file, and to our amazement, they were able to qualify this very quickly. And I think it was like 7 days after Butch had lost the tool, we shifted like the print schedule and uplinked this file, printed the wrench, and there's an amazing image online of Butch. He had no idea we were doing this, so he came to open the door of the printer, and there's the tool that was missing.
Just like magic.
Like magic. And to me, like in that moment, I realized the 3D printer is like a magic box where like you close the door, it's empty, you open it, and the thing you wanted was inside, and there's this like happy picture of Butch holding his wrench. So that became the story of like what the printer did, because it was easy to conceptualize and it didn't have a worm logo on it.
That's so funny. So there's like a technical question about this. Do you have to design a part differently for a 3D printer in 0G versus a 3D printer in 1G?
We had the way we got to this, having a printer on the space station, was it was an interesting process. What happened was the first contract we got was through the Flight Opportunities Program to do zero gravity test flights. No funds exchanged, literally free 0G flights, and we had to show up with all the hardware. And so that was the first contract Made in Space had. But it was the summer of 2011. We had each month we had a flight week. So we had this like 1 week on, 3 weeks to fix hardware, back again in Houston, flying these flights. And we started with the concept of, we're going to make a zero gravity 3D printer, one that just literally doesn't need gravity and maybe does some weird stuff you could think you would do if you didn't need gravity there. And we were like just beating our heads against the wall trying to make this thing work.
Trying to make like a free printing thing that just like comes out in the middle of the, crazy.
So then we thought, and also you have 20 seconds of microgravity between these 2G pullouts, the way the airplane flies. So you go 0G for 20 seconds and then like 40 seconds of a pullout, and then so you have hypergravity. And so what we kind of landed on was, what if we just made a 3D printer that worked independent of whatever gravity you gave it? So it could work in 0G, 1G, half G, 2Gs. And that way we could just run the printer the whole time. And if we got a successful print at the end, we knew it would work in space just as well as it would work in hyper-G. And that just was just like, we were forced that direction because of our environment we were developing in. And that still was really hard, because the 3D printer is, when the news got out we were doing this, we had like every 3D printer company sending us printers saying, can you send my printer to the space station? And what they would always do is they would send us a video where they would turn their printer upside down and they'd say, look, it works upside down. It will work in space. Like, you don't have to do anything. And it was interesting because we got like a dozen 3D printers for free. And then what we did was we just hacked all of them until we could, like, and took parts, and nobody gave us money to build these printers. So we were like hacking these things. But turning the printer upside down doesn't actually tell you it'll work in zero gravity, because you still have gravity there. And the printer is like, has little tiny fluctuations in like the way the belts work or the pulleys. So they all need gravity. And so what we had to do was design, a 3-axis movement that was that could move very precisely without having little, millimeters of fluctuation. It was literally those 3 flight weeks, four flights a day, I guess. And it was the last flight of the last week where we had one more thing to try, and if this didn't work, it wouldn't work, and we'd be out of flights. And we made it work on that last flight. And then that design went forward to NASA into some proposals that led to the contract to develop the
So
printer.
the hardest part was like 3-axis control, like precise enough to not have any give for lack of
because you're
gravity.
like 3D printer is like fractions of a millimeter of precision. So if you have any movement in those in those axes, you're gonna throw off the whole print. So it just ended up being this like really robust 3D printer that used different types of movement mechanisms and actuators than what a typical printer would use. And right after we got that printer flown, we literally cold emailed Admiral Cullum, who was the head of N4, the Navy's logistics and supply chain arm, and said, hey, we're put a 3D printer on the space station. We figure you probably should have these on submarines. And he said, why don't you just come out to the Pentagon and show me what you've got? We brought one of these printers in a Pelican case, wheeled it into the Pentagon and you're at the security line and they're like, what's in the box? And we're like, it's a 3D printer. And they're like, what's a 3D printer? And we're like, it's a device that can make anything. And they're like, all right, come on in. And it's like,
I feel like you get it.
right? And then there
we
a
gun,
right,
yeah.
It was not good. But so we got there, we showed them the printer, we put it on his desk. Fortunately, once we got to him, his team was smart enough to say, like, you can set it here, but don't turn it on. And but we got in front of him and we did some really cool stuff with the Navy and got on some ships and things like that.
That's super cool. Yeah. So, okay, in the beginning of this, I'm sure you guys had a very like sci-fi idea concept of what it could be.
Yeah.
You know, we can print anything anywhere. We can, you know, you don't even have to have anything on the space station. You can just print things as you need them.
Right.
That's it.
Yeah.
By the end of it, I'm curious, like, how far towards that vision do you feel like you got?
Yeah.
Are there like, what were the pieces of the dream that never quite got realized, or did you mostly like kind of get there?
Go way back. I was December of 1999. I was a little kid growing up on the Gulf Coast of Florida, and I, by all means, like, I should have been a marine biologist. I spent more time on my boat as a kid than on land, and exploring like the ocean, kind of falling in love with the natural world and really just wanting to like protect it. And but it was December, I think 19th of 1999, there was a space shuttle launch. And I grew up like a direct line across the state from Cape Canaveral. And the launch was at just after dark. And I had this, I stayed up a little bit late. I went into my front yard to see if I could see this shuttle launch. And sure enough, I saw this like little star going up into the sky. And I just spent my day on my boat. And I was thinking about how these astronauts were on their little boat, leaving the shoreline of Earth and going into the ocean of space, and how they were having this kind of joyful time the way I was having on my boat. And I made this connection that space and Earth are very much a part of one thing, and that maybe the way we solve the big challenges on the planet is to go beyond it and, think outside the box, if you will. I don't think many kids at this age like have any kind of connection like that, but it made me realize the way I wanted to help protect the planet as I got older and went and did work was to do stuff in space. So that set me on that path. It ended up, taking me to go to school near Kennedy Space Center so I could work on the space program, worked on the space shuttle. And then I was working on the space shuttle one summer, and Charlie Bolden showed up, administrator, and gave this very emotional all hands to Kennedy and said, we're retiring the space shuttle and most of you are going to lose your job. And I'm in the back of this this room as the intern, and I'm like, what? Like, I thought I was going to work on the space shuttle my whole career, and felt kind of lost. And that same summer ended up joining a club called ZEDS, which the founders of Astronis also were very big members of. And some of the brightest minds of the space industry today all came out of ZEDS. And I thought it was a model rocket club when I joined it, and then I realized it's like kind of like a secret cult for the future of space. And it was in that group that I was given. They used to hand around like a Bible, the High Frontier, Gerard O'Neill's book about building colonies in space. And I got a copy of the High Frontier, and what that book explains, it was written in the 1970s. Princeton professor who had this kind of question that he posed to his students, which was, is a planetary surface the best place for an expanding technological civilization? And the overwhelming answer was no, we should move beyond planetary surfaces and build these giant like city-sized space stations that have gravity and you could support the growth of humanity that way. And the book kind of outlines how we're going to do that with 1970s technology. And step one was have low-cost launch. And the space shuttle was about to happen. So it was like the idea was the space shuttle would create the low-cost launch, and therefore we would build cities in space. And so I read that book right after I found out the space shuttle was retired, and I was incredibly upset because I wanted the future the book outlined, but the space shuttle going away made it feel like we wouldn't get it. And but then like over the course of the years after that, I realized that we have these commercial launch companies coming online that are actually pushing that basically chapter 1 of the book forward, and I'm going to stand on the shoulders of those giants and build the next step. So with Made in Space, it was, what if you what if you built these big city size, colonies in space there using the materials there? So this is a very long way to get to the question of yours, which is, what was the big vision of Made in Space? And we drew this picture in day 1 of a 3D printer that was like gigantic, and it would 3D print what we called extended structures. And imagine it's just printing a gigantic cylinder that's the diameter of one of these space stations that can rotate and create gravity. And that was always like the kind of the vision of the company, was how do you get to this idea of like zero gravity extended structure printing? And the furthest we got there was shortly before the company was acquired, we won a contract called Archinaut with NASA that would build. We had built one of these extended structure printers that would build. I think we had the Guinness World Record for the longest 3D print. It was like, our office was not as badass as this, but a very long building, and we put the printer on one end, and it just printed across the floor for many days and built this huge structure. And I think we were putting like little wheels under it to hold itself up. And then it was so big, we literally just hoisted it to the ceiling and hung it there because there's no way to get it out. And so we had a contract to fly that on a satellite bus and print the boom that would deploy a solar array. And that was as far as we got. And then the company was acquired, and I felt like a little piece of me died with the sale of that.
Yeah. Was it because you still wanted that dream and you could see a path to get there, or was it that that dream wasn't going to happen for some practical reason or something like that?
I think Made in Space was probably a decade too early. The ideas that we were creating there are definitely the things that will enable these types of futures to happen in space. Is it commercially viable even today? Not really. You don't need that yet. But that actually led to why Outpost is doing what it's doing, because I realized where the real market opportunity is while we did all that. And that's why after we sold Made in Space, why I decided to build Outpost.
Did you decide right after? Like, was it like the next day that you had the idea for Outpost, or did you take a break and think of a lot of ideas and weigh some together?
Yeah, I didn't. It wasn't. When we get into like what Outpost is and why, it definitely was kind of brewing the whole time. But I took like a good 6 months off where I tried not to do anything, and then was really getting like pretty itchy to start another company. I had have a notebook full of ideas, and actually the first thing I did was I pulled my co-founder now of Outpost, Mike Fergala, good friend of mine. I asked him just to like sit down with me and look at all these ideas, and we kind of like mapped them out and created all these weird rankings of like what's a good idea to start, what's a good company. And Outpost just kind of was top of the list. And there was completely non-space companies. Like I was going to start a surf shop. That was one of them.
Nice.
What
did you think of that one?
I mean, he might've been for that one. I was like really close to the surf shop idea. I'm glad I didn't. What happened was I called a bunch of well-known surf shops up and down the LA area, like far enough away that they wouldn't feel like I was competing. And I said, I think I'm going to start a surf shop. Like, what's it like? And they basically all told me not to do it. They're like, it's so hard. Like, you have to buy, you're going to spend $200,000 on inventory. And if you guess the wrong stuff in 3 months, it's going to be out of date. And I was like, I'll make that mistake very quickly. I'm not going to do that.
Totally. And so, okay, instead of surf shop, we decided on Outpost. Do you want to tell the story of kind of the early days and the idea and that thing?
Yeah, sure. So one of the last things we did at Made in Space was we started to have this like concept of most of what we had done up until like for the majority of Made in Space was what we started to call space for space. So things you would make in space for space, things that are unlaunchable, maybe they're too big to launch, too fragile to launch, or you just need them for like the astronaut to survive. Then we started to have this concept of, well, maybe there's some things that are like space for Earth, things that you could make in space for Earth, that maybe has more of immediate market needs. And of course, just, like I said earlier, like someone at NASA had these ideas 20 years prior. So like you go back and read all the ideas of what NASA was thinking about. And one of the ideas that was really interesting was, if there like a whole genre of materials that are crystalline based materials, that if you make them in zero gravity, you get a more perfect crystal and therefore some better property than that material on the ground. And the one that really stood out was fiber optics. Specifically this one type of fiber optic called ZBLAN, which is an acronym for the ingredients like zirconium, barium, lanthanum, aluminum,
Oh, is
sodium.
that really? I've seen that before,
Right.
but I always figured it was local area or like local access network or whatever.
Oh,
Like
that's so funny. I never thought that.
Because fiber. I figured it was like a networking thing.
ZBLAN.
Yeah, ZBLAN is what I've always read it in my
Maybe
head.
that's why a lot of people say it to me as ZBLAN. I'm like, why are you saying it like that? Like,
that's always how
now
I
I
thought
see
of it.
why. I see why.
All right.
Never would have thought that. So anyway, it's a fluoride based fiber, unlike silica based, which is what we use today. And if you look at an attenuation chart of ZBLAN, its theoretical performance matches like the theoretical best any fiber can perform in terms of losses. So it has like the absolute lowest loss you can attenuate light through glass. The problem is that those ingredients, the ZBLAN, it's kind of like Italian salad dressing. And when you heat that glass up and pull a fiber, you're going to get all these separation layers, which create voids and defects. And the crystalline lattice is just messed up and you don't get that pure crystal. So it's made on Earth. It's used for these like far infrared use cases where attenuation's not really the problem. It's more about getting that wavelength that silica can't operate in. And they're short lengths of that fiber, but the holy grail is to make meters and kilometers of it so you can put it into data centers and long-haul telecom and submarine networks. But there's just no way to make ZBLAN at those lengths and still have the quality that would be better than silica by any stretch. Like we're probably 100 times worse than silica right now. So we went to NASA, we formed a kind of a partnership on this, built a machine that we flew to the space station and made some ZBLAN. We brought it back. It was a very small amount, but it was enough to analyze it and see that we actually suppressed crystallization and got a better performing fiber. And then we literally shut the whole project down. And then like a year later, the company was acquired. And the reason we shut it down was it was a really cool science experiment, but we knew that there was no way to commercialize it because you need a factory that can move tons of it back to Earth. If you can't move tonnage, then there's no way to bring it to market at both the scale you need and the cost to compete with silica.
You don't just print one single strand and
right,
just let it go all the way down and
that'd be
just
cool.
roll it in down there.
Yeah, it's like a space elevator.
But in reverse.
Yes.
Yeah.
So that idea like could not escape my brain, that there are materials that you can only manufacture off Earth that have incredibly huge implications and applications on Earth. And the only way to get there is if you have a platform that can get into space, produce this stuff, and bring it back at scale. So when I went back to like the drawing board of what could we work on, the idea of Earth return was like the top of the list, because the return lane from space is non-existent. We've sent over 15,000 tons to orbit in the history of space, and maybe 200 tons have returned. And I like to make, like, all my companies are bets on a future that I feel I can bet on, and it's like very likely to happen. And the bet here with Outpost is that space will have a return lane, and there's going to be a lot of stuff coming back from space. And maybe, like, I would argue we'll get to a point where more things are coming from space to Earth than Earth to space. Like, we're going to send humans to space, but a lot of the stuff is just going to come from space, and we're going to bring stuff back. So whoever builds the return lane is going after an incredibly massive opportunity, and it's just been widely ignored. So that was the bet, and then that led us to, well, if you're going to build a return capability that's focused on large scale down mass, routine flights. You need things that are like a reusable platform, something that has high payload capacity, very precise landing. You don't want to crash into a desert or into an ocean. You need a landing facility that you go to so you can process payloads quickly. So those requirements just stood out as things that are very different than what we've seen in the past.
So you started with that idea of the use case, which is, okay, let's get ZBLAN or whatever. Like, what are the other things that you might want to take back just so people know for like the sake of the requirements here?
I mean, we use ZBLAN as a good example just because it's very public, and there's some that we won't talk about. But I think other ones that are widely discussed are semiconductors, silicon wafers. Pharmaceuticals is in there, but I think it's
tonnage or whatever.
It's a very small like kind of payload capacity. That's where I think it's really interesting, even just those three, like fiber, silicon wafers, semiconductors, because the entire like technology foundation of this planet relies upon these types of materials, and today they're widely not American made, and we are very much dependent on other nations to provide us these materials. So this, like, my belief is, if anything should be American made, it's these types of technologies, and we need to bring that back to America. But the best way to make them is probably not on the planet. It's probably in space. So these need to be American made materials. And it just turns out the best place to make them is like above America, not in America.
Very cool. So, okay. So we're trying to land the world's most advanced technologies, basically come from space, land a lot of them back here on Earth. And so the driving requirements are probably like, well, survivability through the atmosphere, obviously.
Right.
It's the precision of the landing. Like you said, you want to not crash into an ocean and have all your stuff just like impact and smash into the water. What are the other like driving requirements that led you to the solution that you ultimately built?
I mean, you got like the two that are really important. So it's like precision landing, safe reentry. We need a very precise microgravity environment to produce this. I can talk about that, why the space station was not good for that. And then the other one is reusability. So if we make a platform that is single use, it's just going to cost too much. But if we can make a reusable one, then we get the cost unit economics to be competitive with terrestrial made products.
I'm very curious about the microgravity thing. My assumption, just like knowing nothing, is that, okay, once you get certain altitude, then you start experiencing microgravity in a certain way, and it's not dependent on having walls around you for the ISS. Or I get, maybe if it's pressurized, is that the difference? I don't know.
No. So what we found, I think this is like, I feel like this is like a very like not widely known piece of like what's happening on space stations. So when we were 3D printing and making fiber on the space station, what we found was that having astronauts there was really detrimental to what we were trying to do. The first thing is you can't kill an astronaut. Like, that's kind of an obvious rule.
A driving requirement of lots of things.
It's so much like NASA has two driving requirements: don't harm the astronauts and don't harm the space station. And from that, they derive hundreds of requirements. So when we go to NASA and say we're going to put a 3D printer on the space station, on top of all of our requirements, they levy probably 200 additional requirements. And to meet those requirements means a lot of extra time and money. You're doing tons of testing. You're developing things with materials and coatings and all of these different things just to be super safe. So it takes an incredibly long time to fly something to the space station for that reason. And as a startup, you want to iterate quickly, iterate often, and flying to the space station is not the place to go if you're going to iterate fast. So that first just kind of, put a thorn in our side for flying stuff to the space station. Once we got there, what we found from our accelerometers on board was that anytime the astronauts were awake, they were creating little fluctuations in the gravity environment.
Fascinating.
They're bumping around, and
is it the shock of footsteps, or what? Not footsteps, but obviously,
it's just
but like
their movement,
bumping the walls and stuff.
Our printer was next to the treadmill And anytime they were on the treadmill, you would measure their accelerations.
Wow.
The life support system alone creates little fluctuations in the gravity environment. So the only thing we could do was wait for them to sleep to do all of our operations. So our schedule was built around their sleep schedule. And it still wasn't perfect, but we got at least like the treadmill out of the picture. So what I realized was, hold on a second, there's a lot of the value of what we've been talking about doing on space stations has nothing to do with humans. We're talking about all these other things like space manufacturing. And the little secret is that not only do you not need humans there, you don't want humans there. What you want are autonomous space factories to do all this work. So by designing a platform specifically for this, we can design something to, one is on orbit, to create a very pure microgravity environment. And that's where we start. Now, there's other things we can do also, like we can create a more pure vacuum environment in space. You think of space as having a vacuum, but you can actually control the level of vacuum doing certain things. So we can create a more pure vacuum on our platform than what like the space station would have outside of it.
Wow, interesting. So, okay, the microgravity. So, if I understand that right, the shock of an astronaut jumping on the treadmill, the worst place possible to put is right next to the treadmill. That's crazy that they chose that. But or like probably chose that for you.
Yeah.
But so like people moving on the treadmill or other bumping around and things means that those little tiny imperfections enter the product. So do you have to design your product now around that? Like don't have moving arms or whatever the hell that create the same sort of like fluctuations and movements.
Right.
And is that a requirement?
The 3D printers have a lot of like degrees of freedom, so there is some movement there. I think a lot of the manufacturing techniques that like for making fiber and things can be done in a way that you're not creating too much gravity fluctuations. These are small mechanisms compared to like a human body, a treadmill, big life support systems and things like that. So, or even like the orbital boosting of the space station creates, I mean, that's a big one. Like there's videos online of like, the orbital boosting, you see like they're floating, something fly. Yeah.
What's the deal with the big, huge cube of metal that's on the space station?
Dude, I have no idea. What was that?
It was like tungsten or something. I forget what it was.
Somebody was joking. It's like they got a rod from God on the space station.
Well, that's what with the whole ISS deorbit thing.
Right.
Is that, have they modeled that? Hopefully, like the gigantic cube of metal that's in the space station. Like that's, I don't know. That feels like it's gonna land.
Yeah, I think that's like a whole nother podcast you should do. Figure that one out.
I know. Well, I actually do it. I would love your opinion on whether we should deorbit the International Space Station or not. But maybe that is another podcast for another
I think
time.
that like with Carryall Outpost return vehicle, we could probably go get a module and bring it back.
That'd be cool.
And like I think that would be, I think somebody should fund a mission to return at least a module and put it in the Air and Space Museum, and like Columbus modules there, and you get to like see the real thing.
Yeah, absolutely. Okay, good. I'm on that team.
Yes.
Well, we should talk about that. Okay, so one of the driving requirements is gravity. Another of the driving requirements, maybe like the simplest way, we haven't really talked that much about what it is or what it looks like yet. So maybe let's talk about how it breaks into the atmosphere and like the sort of what the profile looks like as it comes through the atmosphere and then lands on Earth, just so people know what the hell it is.
Okay. So the kind of the general idea for Earth return or for reentry is governed by like one of the most common like equations that we look at is called the ballistic coefficient. It's a measurement of the mass of the vehicle divided by its surface area. So something like the space shuttle had a very high ballistic coefficient. It comes in super fast. It's transitioning to subsonic, very low in the atmosphere. A capsule like Dragon is going to be a little bit lower ballistic coefficient. It's going to, because it has, more of a dense shape. The challenge with reentry is that you have a very large dispersion on the ground of where you'll land. And if you do nothing about this dispersion, it can be kilometers across. So meaning you re-enter and you're anywhere within like a many kilometer ellipse of uncertainty. And that's not helpful. That's very dangerous. So when you look at something like a space shuttle or Dragon, what's being done is extra propellant is carried and course corrections are made on the way in to fine tune that dispersion and make a smaller landing ellipse. The Dragon lands in the ocean with maybe like a 5 kilometer radius when it comes in. So it's easy enough to have a ship nearby to go pick it up. Um, that's all at the expense of payload. You don't want to carry extra fuel. You want that to be your payload. And the smaller you go in your vehicle, the more that payload fraction gets disrupted. You have less payload, more fuel. So we wanted to solve that and have a way to get landing pad precision, so better than anything we see right now, while carrying the most payload capacity, right? Not like, like 50% payload would be the target. So the best way to do that is to have a very low ballistic coefficient reentry, because then you can transition to subsonic higher in the atmosphere. And instead of being ballistic and supersonic way low and then popping a parachute open at the last minute, you get to do this. You get all this altitude to decide where you're at and get to the landing site. So that's our first stage of our system, is a deployable heat shield. And what this does is it allows us to build something more of a satellite than a capsule or a space plane, because the heat shield is folded up and it pops open like a big dinner plate, basically, with a saucer on top. That we re-enter, now we have this big surface area heat shield with our satellite vehicle behind it. It slows us down high in the atmosphere. We transition to subsonic higher. So we'll be subsonic around 90,000 feet. And a drogue will slow us down a little bit more. By 65,000 feet, we open our second stage of reentry, which is a paraglider. So rather than use parafoils and parachutes, which is what we're all used to seeing, we went with a paraglider wing. It's a single surface ripstop nylon fabric. We know this because Mike, my co-founder, is a paragliding pilot and aerospace engineer, paragliding pilot. And no one really ever looked at a paraglider for this use case, because what you do with paragliders is you put them in a backpack, you hike to the top of a mountain, you pop the wing open while standing still, and then kind of like gently walk off the mountain and fly away. They're not, traditionally used for dynamic deployments in the upper atmosphere. What Mike realized that most people hadn't is that over the last 5 to 10 years, the advancements in the material technology have improved so much that the mass of these wings has dropped significantly. So we're like in the 2 kilogram range for a wing big enough for our satellite, packs into a little volume like the size of a kid's backpack. And the paragliding community they've made them lighter because they have to hike up mountains, so they don't want to carry weight. But they're also doing like acrobatic stunts with their wings and putting high G loads on them. So all of the lines are rated for high G loads, the stitching's high G. So this all starts to suggest like, well, you could get pretty high G dynamic deployments if you could just figure out how to make these open. And now there's a big question: can you make a fabric wing open at 65,000 feet? Is there even enough atmosphere to do it? The experts told us that was not possible. So we built a small wing and put it on a weather balloon, took it up to 65,000, dropped it, deployed it, and we were able to get the wings to open. And that was like the first proof point for Outpost, was that we know that the low ballistic coefficient heat shields work. NASA developed and has flown those. So the question was, could you make a wing open high enough up that you would still have all that altitude to have the control authority to get to a landing site? Because the wings have, the paraglider has like a 10-to-1 glide ratio. A parafoil is like 3-to-1. So huge amount of glide out of these wings. And with a robot flying it, you can control it. So we knew if we could just get the wing open, then we could fly it to the landing site. And that's what we spent the last few years doing, is just, we've moved up to the full scale wing. We've done drops at those altitudes, and now we're just like hitting the target with that system.
So cool. So if you're a space person, which like we are, but maybe not all the audiences, that deployments are scary. Like a deployment is, so like when we launched our 4 satellites recently, like we're obviously watching really closely to see like, okay, are the solar arrays opening? Are the reflectors opening? Whatever. And those moments are tense and nerve wracking. Cause I mean, I don't know. There's so many ways they can go wrong and only one way then they can go right. So to design something with 2 deployments, like 2 different deployments, the deployment of the heat shield and then also the deployment of the wings is, like, scary for various reasons, but the trade-off is good enough so that you chose it. So, like, I guess the only question in that is, like, how do you reduce that risk for yourself, or how do you convince yourself that the risk is worth it to get the trade-off from the
Right.
trade-off of the risk that you're assuming?
That's a good question. We looked at, I mean, first we looked at the other options, like, do you build a capsule? Well, if we do, we're not going to get the payload capacity we need, and most likely not the landing accuracy we need. And it will be more of an abrupt landing, so that the chance of refurbishment of the vehicle is less likely. Um, Also, I should have mentioned this earlier, but one of our goals is just kind of company goals is very much focused on sustainability. And I, I feel like we have an opportunity to make the space frontier a little bit different than other frontiers of the past. Um, and part of how we do that is we want to make the entire vehicle reusable. If we had like a spacecraft bus as a kick stage that kicked our reentry capsule into orbit, and we burn up the kick stage, now we're leaving trash on orbit, or at the very best burning it up in the atmosphere. We want to bring the whole thing back. And if we can do that, we're going to make a far cheaper spacecraft at the end of the day, because a bus easily is many millions of dollars. So um capsule, you're not going to get the bus back, you're just going to get the capsule back. So um we forced ourselves into this position of designing something that's going to get the whole vehicle back, um which then just led to, well, what is the lowest risk way to make, the heat shield's probably the more tricky deployment system than the wing. So how do you design the heat shield so that you have um a very low risk deployment? And I think we're there. Like, we're leveraging a lot of work NASA's already done that's been flight proven,
Have you
adding on
talked
to
about
it.
what the actual deployment mechanism is for that?
Yeah, so a little bit. We started with looking at a inflatable heat shield, which similar to like NASA's HIAD, the hypersonic inflatable aerodynamic decelerators. Um, and then they did lofted mission in 2022, which kind of demonstrated that. We looked at that for a while. I think that it has some merit. The inflation systems are pretty cumbersome, so we wanted to go towards a mechanical deployment system, which looks, NASA developed one of those. They called it ADEPT, and did some flight testing with ADEPT, where you have a mechanical arms that deploy, and you have a fabric heat shield made of well, there's a few different fabrics: 3D woven, carbon fiber, Nextel, silicon carbide, like different, depending on your price appetite, different materials you can go with. But the mechanical actuators are, we can design those to be pretty reliable and redundant. And we actually open the heat shield early. So like, we get on orbit, we open the heat shield well before we do a reentry. And that gives us time to make sure everything's open. It's not like the last second pop the heat shield open.
Wondering that though, because like when you are the way that I would think about it is, okay, when the space shuttle was designed, there was like this risk that it would like bounce off the
Right.
atmosphere or
Yeah.
something. So I was wondering, do you have to like get sufficiently into the atmosphere before you deploy the thing? It sounds like no, you can deploy it and then
Yeah.
re-enter. Is that like what
Yep.
what causes, is that just like a surface area thing and you guys are below some minimum or maximum surface
Yeah, it has a
area?
lot to do with just like the reentry angle and the velocities that you're using. So we're designing just to have a enough delta V to get that reentry precise enough to not have that. The the space shuttle, like, bouncing off the atmosphere, is actually an interesting problem to study, which is the idea of like atmospheric skipping. So there is a way to burn off orbital energy in a more efficient manner, where you actually skip off the atmosphere, come back up, and come back in. Like, remember, like, in Super Mario World, when he flies with the cape, and you
Yeah.
can kind of like bounce while he's
Sure,
flying.
yeah.
You can kind of do that. Those are, I think that's like for the future of Earth return, where you start to get like a lot more interesting on how you do your reentry, in a way that uses less propellant and lower mass systems, and just like take advantage of the atmosphere to slow yourself down. But so the shuttle had that huge belly that created that like general concern. but we don't have that with the shape of our vehicle.
And you guys don't have any active maneuvering or whatever on the thing. It's just the steering of the wings, basically. There's not any other propulsion on the thing.
After we deploy the wing, you mean, or on the reentry?
Well, on the reentry.
So we spin stabilize for the reentry portion, and that helps us just be stable. And then once we're into the atmosphere, the heat shield folds back up, the wing deploys open, and then the wing is being controlled. So there's the trailing edge has lines on it, and our robot is pulling on that and steering the wing.
Cool. But then it just glides and lands on a long runway.
Yeah, so it's not propulsive, if that's what you're asking. Like it's just using free flight to maneuver. No runway though. Like we can touch down on like a very small little target. So
really?
Yep.
Okay.
You can watch videos of like human paragliders like landing on a little floating pad on a lake. So like, we're not as good as the human yet, but theoretically you can hit really small targets. So we come in and we just like flare at the last second and then set ourselves down.
Very cool.
By developing this platform as like a high payload capacity, precise landing technology, we're not just enabling factories to go to space, manufacture things and come back, but we're enabling supplies and cargo to go to space and come back. And we don't have to come back to the same place that we launched from. So some of our most earliest use cases are through our partnership with the Department of Defense to get supplies around the world quickly. So you can imagine having a carry-all with a shipping container payload loaded up with supplies at Cape Canaveral, launch it on a Falcon 9 or a Starship, and really like within an hour or two, you could be landed somewhere else on the planet. And this changes how we respond to global threats, how we put supplies into critical areas that are contested and hard to get to. And it's one of the areas that we're really focused on, because I think like we can be like a life-saving organization within Outpost if we do this right. Because today when a group of Marines in a forward operating base needs something, you put in a lot of military personnel at risk to get there, whether it's an aircraft coming in to do an airdrop, a naval ship doing logistics into those locations. There's lots of personnel being put into risk to get people what they need. And we see the future where you don't have to do that. The warehouse is at Cape Canaveral, not in the South Pacific. It's easier to maintain the warehouse. You get it on the launch vehicle, you hit launch, and 60 minutes later, you're re-entering over the site and then landing it with incredibly high precision in front of the person who needs it. So that, like, it's literally the same exact platform that's going to enable these commercial markets, goes after something that's going to help our military.
MREs from God, basically.
Yeah.
That's sweet. So I was wondering about that as a use case, because my understanding, maybe this is wrong, is that your landing would be slower than just a capsule or something that's like a harder reentry vehicle or whatever, like a lower or a higher ballistic coefficient, a higher ballistic coefficient entry vehicle. And so it would come down slower and then therefore could be like shot down or something more easily. And so I was wondering about that as a use case. I don't know.
Yeah. So I think like it's important to make our systems clearly designated for use cases that you wouldn't shoot down. And, the complete like flip side of this argument is, if you're re-entering capsules or very high ballistic coefficient vehicles to supply things, they're going to look like missiles, and those will get targeted. But by being very public about what this is and how it's not being used to deploy weapons, it's being used to supply important supplies. I think it could be purposefully not targeted. And but that said, like there are ways to get these in without being noticed, and we don't talk about that, but there's ways that you if you need to get it there without being noticed, you could do that.
Interesting. Okay, so I'm curious too, just about how you prototype something like this. So you talked a little bit about this before, where you took the wing up on a balloon and you flew it. Where on the development process are you? Like, what have you built so far? What are the next milestones you have to hit? I would just love to learn about the R&D, basically.
So we are very, very hardware rich and like get out and test as quick as possible mentality. So the first thing we did was we did these small scale weather balloon flights to just know that the wing could work. And that gave us some proof point there. Then we built and flew 2 satellites to space, just to get heritage on essentially the brain of our vehicle. That alone was a pretty like ambitious endeavor. We booked our first launch with 7 months before flight, and we had a whiteboard design of the satellite. And it was such an ambitious schedule that every day somebody on the team felt like this was failure. There's no way we would make it to the launch pad. So we named that mission failure is an option, to be like incredibly clear publicly that we expect it not to work and we're still just going to try. And there was many days where it seemed like it was over, but we made it to orbit. We got the satellite up, it worked. And then we were silly enough to book, that was a Transporter 8 flight. We were silly enough to book Transporter 9 as well, thinking, well, we're going to build more than one satellite, so we'll kind of like take lessons learned and get the second one up. In the end, we had literally 1 month between launch of Transporter 8 and when we had to turn over all the paperwork for Transporter 9. So we built and qualified our second satellite in 1 month and flew it.
That's crazy.
And that one sold the payload spot to NASA and had to build the payload. So
cool.
That was insane. But we got 2 satellites up in 2023 on that incredibly fast schedule. And very simple satellites like the Sputnik for Outpost, but it taught the team everything about how do you move through the process, how do you get all the stuff we don't talk about, like FCC licenses and setting up ground stations and all that fun stuff. So we did all that. Then this past year, we spent our time on the full scale paraglider system and doing, we set up a test site in Mojave where we were out, every few months with a helicopter and doing all these different drops scenarios to perfect our wing deployments, consistency of deployments, targeting, and then doing the high altitude weather balloon drops as well. So at this point, we've retired all the key risks of the technology. And right now we're working on building the first mission for orbital return. So we sold 4 missions to the military. And so we're on a schedule right now to fly 4 missions in 4 years. And the first one in 2 years from now. So right now we're just on that critical path of getting to first flight. Totally. The satellite.
So you demonstrated the wings, you've demonstrated the brain, like the satellite brains, the bus, basically. Yeah. But then what about the heat shield or the shield?
Yeah, so the heat shield, like we're leveraging through a Space Act agreement with NASA, their flight heritage of the heat shield. So nice. A huge amount of data that NASA has, both from like flight heritage, arc jet testing, all their simulations, material testing. So
did they fly one?
Yeah. So ADEP flew in, I think, 2018.
Oh,
and then
recently. Yep, and this wasn't like a 1970s paper.
No. This is very recent. Okay. And then there was the inflatable heat shields although we're not doing inflatable, the ballistic coefficient and a lot of the simulations are pretty relatable. And that there's a lot of heritage there between lofted and then the earlier IRVI missions that NASA flew. So we're just leveraging through partnership with NASA all of that flight heritage.
Awesome. Is there anything else that we haven't covered yet that you want to cover?
I mean, I think we covered everything. This doesn't have to be part of the podcast, but I'm very curious, like how you balance, like being a great dad, which is very clear you are, with the demands of work, because that's something.
Do you have kids?
I have 2 kids. That's something I work really hard on and focus a lot of like culture building in the company on how do you create that balance and show that the balance is actually the important part about how to show up and be your best for your team and also show up and be your best for your family. Totally. So how do you do it?
Oh man, that's like the nicest question. So first of all, thank you. But no, I just try to involve him in as many things as I can. You
Yeah.
know, he's one. He doesn't
Okay.
know anything. Like he doesn't know what's going on. But I've already
Well, he's
taken
gonna
like
watch this one day and he's gonna be like, "What?
I know.
I
Well, yeah,
know
that's right.
exactly what you were
You know
talking about."
nothing, little kid. No,
You
no,
brought him
he
to the
like
launch,
I
right?
did. So he's seen now over his first year of life. I took him to a he's seen an chronoplan in person, so like a surface effect vehicle.
Whoa.
He's seen we went out to Joby, so
I
he
love
saw an
Joby.
eVTOL. We took him to the Hermeus factory. They'd already taken their plane out, so we saw the demo vehicle
Okay.
for Hermeus. He's been to ZipLAN, so he's seen the drones, the new ones. Have you seen the new ones yet?
Yeah,
They're
that's
super
awesome.
cool. They're super cool. And he's seen a rocket. So that's a pretty solid first year of life, I think.
Yeah.
And it's been super fun just to involve him and get him to see all these things.
That's awesome.
Yeah, I love it, dude.
Okay. So your answer to the balance is actually involve.
Just bring him in. Yeah.
Bring him in.
Yeah,
Cool.
yeah, totally.
That's awesome.
He hasn't really been here for a day of work yet, but he needs to. I need to bring him by.
Oh,
He's
yeah.
been for the holiday party. He's a hit. But
when he gets older, he'll want to be like my 6-year-old is convinced that he is the satellite engineer at Outpost, and
nice.
he's like that he has designed the satellites that are in space. And
I think that's probably true.
There's definitely some whiteboard drawings that he did. So
nice.
Yeah.
Key part. Awesome.
Yeah.
Well, thank you so much for coming on the show, man. This is
Thank you.
really fun.
Yeah, it's a pleasure.